Exercise 54. Recall that in exercise 53, we derived a formula for cos A minus B from the law of cosines. In this one, we have to do something similar, but now we have to derive the formula for cos A plus B. So, using the law of cosines and from a figure similar to what we saw in exercise 53. So, let's see what we can do. Now, instead of the difference of two angles A and B, we have the sum. So, let's draw the unit circle, and then from that we will see where things go. So, this is our x-axis. This is the y-axis. And let me just draw the circle as best as I can. Okay, so roughly you consider this as the unit circle centered at the origin. Now, we have two angles, right? And the terminal rays of these angles can in fact be in any quadrant for both the angles. For each one of them, its terminal ray can be in any quadrant. So actually many cases arise. So we are just going to look at one of those cases. The others can be similarly handled and are left to you. If you are suspicious about the method working in the other cases, then you can in fact see for yourself. You will see that ultimately things will work and you will end up deriving the formula for cos A plus B that you already know. Okay, so say this is our angle A. So already we are assuming something. Note that we are assuming that A is positive. So A may be negative also. A can be anything. And then what we do, we call, okay, let me just remove this one. Then from this terminal ray, if we start our rotation and move further, then we have angle B. Okay. On the other hand, we can do something else. We can consider this. But now our rotation is clockwise and is again starting from the positive direction of the x-axis. And now this new angle we have taken to be equal to minus B. Because this was positive rotation, this is negative rotation. But the magnitude is same. The magnitude is equal to B. Okay. Now next what we do, we join these ends of those terminal rays. And we are now going to give some names to these vertices. You can already see that we have a triangle. And the origin of course can be called O, whereas these points, let me call them C and D. Now it is this triangle OCD on which we are going to apply the law of cosines. But how? Exactly how? We are going to concentrate on this angle, angle COD. So that requires us to find what that angle actually is. But before we do that, you just note one thing. Because our angle A starts here and its terminal ray is this, so this point has the coordinates cos A, sin A by the definition of cos A and sin A. Similarly, this point D has the coordinates, because this is minus B, cos minus B, sin minus B, which if we just use the elementary properties of cosine and sine function, that if you have minus B here, that is the same as cos B, and if you have sine minus B, that is the same as minus sin B. With that, the point now becomes this. Okay. Now we are going to try to see what this angle will be, angle COD. So I am not in fact going to write things systematically like how we should write in a solution. All those things, they let us draw the unit circle and let us put the angles in this way, because you see we have in fact identified the angle A in its standard position where the initial ray coincides with the x-axis, but the angle B, the way we have done it is not in the standard position. So when you are writing the solution, you have to actually write these things, that say we are putting the angle B in such a way so that its vertex lies at the origin, that is true, but its initial ray coincides with the terminal ray of the angle A, and then of course it also has its final ray. Fine. So now our aim is to know what this angle COD is. Now we already know that if you add up all these angles, all the four angles, what four angles? A, B, minus B, I mean I am talking only about the magnitude. Okay, so A, B, another B, and this one which we don't really know, this DO, and I mean in between these two lines. So we can do one of these two things. You can either name this point or you can just call this angle something. Let me just call this angle, say theta. That means you understand what angle I am talking about. Three angles we have already shown, theta is the fourth one, this smaller one. And O I can say put here, and this is our minus. It looks a bit cluttered, but you understand what we have done. Okay, fine. So if we now add up these four angles, their magnitudes, then we should get 360 degrees, that is 2 pi radians. That means we have this theta plus B plus A is 2 pi. So this gives us what? Theta plus B is 2 pi minus A plus B. 1b we have kept here and 1b we have taken on that side. So that means our angle COD is 2 pi minus A plus B. Okay. Now, besides these elementary properties of cosine and sine function, that you have these things, you also know that cosine of 2 pi minus a plus b is just simply cosine of a plus b. So now we are in a position to apply the law of cosines on the triangle OCD. So let me just write, for at least for this one, applying the law of cosines to triangle OCD, we get what? And that too, we are concentrating on the triangle COD, the angle COD. So we are going to get this: CD squared is equal to OC squared plus OD squared minus 2 times OC times OD times cos angle COD. That is the law of cosines, right? So now, how are we going to get these side lengths? Two of these side lengths are just one, namely OC and OD, because we have considered the unit circle, and these are two radii of the circle. Two radii means geometrically two radii. The value is of course 1. And the other side length we are going to get using these coordinates and the distance formula. So if we use the distance formula directly, because now we will have to get rid of the figure, so let's just do whatever we want to do with these things in this line itself. So cos A minus cos B whole square, because we are not dealing with the distance CD itself but rather its square, so that square root does not appear. So cos A minus cos B whole square plus sin A minus sin B, that means sin A plus sin B, plus sin B whole square, that is equal to OC and OD are both equal to 1. So 1 square plus 1 square minus 2 times 1 times 1 times cos A plus B, where we are using the fact that cos 2 pi minus theta is cos theta, which is something that follows directly from the definition of cosine itself. You think of the geometric definition of cosine, that means its actual definition. There itself you will see why cos 2 pi minus theta is cos theta. And in fact, you can get that same conclusion this way also, because we have already said that we know cos minus b is cos b. So cos 2 pi minus theta is cos minus theta. This is coming from the periodicity of the cosine function and from the knowledge that its period is 2 pi. So that's why you get cos minus theta, which because of this is just cos theta. So think of this theta may clash with that theta, but you understand this is some angle theta prime. Say. Now think of a plus b in place of theta prime and you get this thing. So now we are going to go forward and see what we are getting. So now if you expand the squares, you get this cos square b minus 2 cos A cos B, and expanding that one we get sin square A plus sin square B plus 2 sin A sin B. On this side we have 2 minus 2 cos A plus B. Let us be a little brief. Cos square A plus sin square A is going to give us 1. Again, cos square B plus sin square B is going to give us another 1. These two ones give us 2, and we have 2 on this side also, so they cancel out. And we are left with this. Minus 2 cos A plus B. Now we divide on both sides by minus 2. Doing that and interchanging the sides, we get what we were seeking, namely cos A plus B. Keep in mind we are dividing by minus 2, so this one will become cos A cos B, and this one will become minus sin A sin B. So this way, from the law of cosines applied to a particular type of triangle, we have been able to derive the formula for cos A plus B. So I urge you to look at the other cases also. There may be many cases depending on what A and B actually are. Actually are means in the sense what their signs are relative to each other. Also depending on what their magnitudes are, in which quadrant they lie, how that affects the relative position of the two terminal rays. All those things you can see, and you will see that ultimately in all those cases, the more you see, the more you get convinced that in whatever case you may have, you may find yourself there, this formula continues to be true. Okay, so that's how one derives the formula for cos A plus B also from the law of cosines. The next two exercises are, of course, as you may have already seen, they are entirely calculation oriented. In fact, they are marked with this word calculator. You need a calculator to be able to solve this. Like this. You see this word. A triangle has sides. A equal to 2 and B equal to 3, and angle C equal to 60 degrees. Find the length of the sides. I think the ink is not enough. So two sides are given and the angle between those two sides is also given. we have to find the third side. That means we have to apply the law of cosines. So the law of cosines in this case gives us this: c squared equal to a squared plus b squared minus 2ab cos c. And that's just it. You just substitute the values for a, b and c, and you will find that c comes out to be equal to square root of 7, whose approximate value you can find using the calculator. In fact, this is where you need to use your calculating device. And a similar one is also given after this, where the angle, however, is not a standard one. So to find the cosine of that angle, there itself you need your calculator. I am, however, going to write the statement of the exercise. The language is exactly same. A triangle has sides. There is really no point in writing something else other than a, b and that other angle. I mean, what I'm trying to say here is that you can call this b and this c and this say capital A. Nothing essentially changes. So here a and b are the same, 2 and 3. And angle C this time is 40 degree. So cos 40 is not as a standard value. Find the length again. Of side C, which you can do similarly. Okay, so I am not going to say anything more about this. And now next let us see 57. Now we come to the law of sines. We have seen the law of cosines, but there is a law of sines also. That's the name, and now the statement is this: the law of sines says that if A, B and C are the sides, are the sides opposite the angles A, B and C respectively in a triangle, of course. Then sine, okay, so the sines have been kept in the numerator. It does not matter. Divided by A, that is equal to sine B divided by B, that is equal to sine C divided by C. That means the sides are in the same ratio as the sines of the angles are. Okay, where we are talking about the angles opposite to those sides. I mean, in that order, the angles are being considered. So we have sine A divided by A equal to sine B by B equal to sine C divided by C. And okay, so that is the law of sines. Now two figures are given, and from these figures we have been asked to verify this, establish this law. And those two figures are just these, which are actually two cases for the same situation. Okay, so we see two triangles. One of them has all its angles acute and the other has one of the angles obtuse. So these are the vertices, and the vertices also denote the corresponding angles also in these corners. Oh, I forgot to draw this perpendicular. There is a perpendicular drawn from the point A or from the vertex A to the opposite side, which has length h. Here also A, B, C, this perpendicular has length h, and the angles have been named. Similarly, the sides are also named depending on which is opposite to which angle. For example, the side opposite to angle A is having length A, the one opposite to B is having length B, and this one has length C. Here also similarly, this is a BC is A, AC is B, and AB is C. Now we continue. Now we need to say what we have to do here. Use the above figures and the identity excuse me, and the identity is sine pi minus theta equal to sine theta. If required, to derive the law. Okay, so that means we are going to need the figure. So we start our solution from here itself. But again, I am repeating that to save time, I am not writing many things. In an actual solution, you have to in fact again draw the figure and explain everything. And then along with those explanations, you write your equations or inequalities, whatever mathematical you have, in their proper places. That only is as an actual proper solution. So in the name of solution, actually really I am just simply giving some hints, that's all. The hints are elaborate, we know, but still they are not, truly speaking, strictly speaking, these are not solutions. A solution must be properly written and should be full, it should be complete. Okay. So now what we are going to see here is we have to derive this from these two situations. So let us consider the acute angle situation first. We see that we are looking at two right angled triangles here. In order to make things more clear, let me call the foot of this perpendicular D. So that means we are now dealing with these two right angled triangles, ABD and ACD. So from triangle ABD and triangle ACD, we are trying to write whatever we get for sine B and sine C from these two triangles, sine B and sine C. So from this triangle we have written ABD first. So what will sine B be? Sine B is perpendicular divided by hypotenuse. So sine B is H divided by C. And from this one, similarly, sine C is going to be H divided by B. Hence, so we get this C sine B is equal to H, but at the same time from this second equation, H is also equal to B sine C, or sine B divided by B is equal to sine C divided by C. Okay, so we seem to have got only a part of what we want, but that too only in this case. So now we have to look at this one also. So to distinguish this one from this, let me call the foot of this perpendicular D prime. And in fact, let us just imagine that we have this triangle actually. In the text, the authors have simply drawn one small line segment in order to show where the foot of the perpendicular is, or where the perpendicular from A stops. But we can of course extend that to complete the triangle, which we have done that. So now we are going to look at again two right angle triangles, but this time the names I think are going to be similar, ABD prime and ACD prime. So that when we are considering ABD prime, we of course are considering the angle B, but when we are considering ACD prime, we are actually considering this angle, which is really not C, this is C, but this then is pi minus C, and that's why this has been mentioned. Again, from triangle ABD prime and ACD prime, we get, See, sometimes due to laziness, we may think that if we just simply write like this, anyone would understand, right? Of course, anyone who knows these things will understand what we are trying to mean, but still, presentation is necessary, and that's why I am stressing on writing a complete solution. It may not feel like a very big difference is going to be made by doing that, but when you go to higher parts of mathematics, when things become more and more complicated, more obscure, then if you do not write a complete solution, two things will happen, at least two very bad things will happen. The first bad thing is that if you communicate your solution to someone who is going to look at that for the first time, they may not be able to understand anything. And because the situation is so complicated, they may miss some points. And the other bad thing, which in fact is even worse, is that when later in future you yourself come back to your solution, you will see this has actually happened to me. Okay. Although I do not deal with very high-end mathematics or anything like that, just college level mathematics. I come back to a solution, and due to my own laziness or sloppiness, I forgot to write some details, and those details turned out to be crucial details. I have lost at least two solutions like that, okay, completely. Still I haven't been able to solve them because that thing is gone due to my own laziness. So whenever you are writing something, if you want to keep it for future or for anything else, you please write it completely. So now we resume. So we are going to get from these two triangles, from this one of course we just simply get this sine B is equal to perpendicular h divided by hypotenuse, same thing here also, h divided by c. And what about this one? From this one we are going to get, actually we will get sine pi minus c, but that is equal to sine c. And that equals again perpendicular divided by hypotenuse b. So you can see that again you are going to finally get this. Thus here also, let me continue like this. Thus here also we get sine B divided by B is equal to sine C divided by C. Okay. Now I am going to write something which will seem like I am just simply giving up and just simply somehow I am writing that the solution is over. So from should I write generality of the situation or from symmetry? I can write symmetry, and in fact that's what I have to explain to you. So from symmetry we get and hence you have in fact ended up deriving the law of sines. But what is this? We haven't done anything with sine A, right? And what does this mean? So from symmetry, See, you should understand that something has happened here. We have drawn our, since this case is a little complicated, let's just not think of it for now. You think of this acute angled case. You have drawn a, or rather the authors have drawn a perpendicular from A to the other side, and that gives us this. Had we drawn a perpendicular from, say, C to this opposite side, the length of this new perpendicular may not be equal to h. In fact, in general it will be different from h, some h prime, say. Now if you repeat this argument with this perpendicular, you will then end up, if you similarly follow the argument, proving that sine A divided by A is equal to sine B divided by B. How can I say that? That's because you see, in this situation what we actually did here, we have ended up getting the sines of these two angles which through which the perpendicular was not passing. This time the perpendicular is passing through the angle C. So we would have these two angles A and B. Now, do we really not need to prove this other thing? Actually, there is no need. Why is that so? That is because the situation is symmetric. Symmetric in what sense? Symmetric in the sense, you see, you do not think that somehow the angles are having the same value or the sides are equal. Not that kind of symmetry, but the symmetry in the argument, in these two arguments that you would have if you also do the other one, that allows us to also have this. Why are the two arguments symmetric, or in fact exactly similar to each other? That's because in order to derive this part of our final thing, we have used this perpendicular. Fine, we have used this perpendicular. If we use the other perpendicular, that is really another perpendicular with a possibly different length. But the point here is that only the fact that these two quantities are equal is where we need this perpendicular, or rather its length. Any special value of the length, that is not playing any role here in this proof. It does not matter whether the perpendicular is very small or very long. The only thing is that it has been used in this argument in a way that it is used and then it is gone also. The moment you make this conclusion, it is gone, because it's gone here itself. It vanishes in the middle, and ultimately what you need is this thing, that C sine B is equal to B sine C. A similar argument would give you A sine B equal to B sine A, or rather I should say like this, B sine A, and both of them will be equal to H prime. So that kind of symmetry, where these names given to these angles can actually be interchanged. Any two of them can be interchanged, keeping the other corresponding changes also in mind. You can change the thing and the argument will not lose its logical validity. That's what we mean when we say, so from symmetry we get this. So this in fact very nicely complements what I said just now, that we should write a detailed solution. Fine, but not to the point of becoming riddled with unnecessary details. You see, detailed solution does not mean you have to just go on writing essays and essays on these things. You should write an efficient solution which has all the necessary details, but also whenever it is needed you can compress things like this. if you can in fact write the other part of the proof involving this h prime, but really that is not necessary. At this level it may feel somewhat difficult to decide on what to do, but with experience you will know what to show and what not to show. It's an art, but it comes with time and practice. So there we have our law of sines. Now after this there are some exercises, again some calculation exercises are there, that is the ones where you will need calculators, and after that there are some theoretical exercises which need your computer algebra systems. So those are in fact computational ones, so those I leave to you. So our trigonometry exercises are over. So from the next calculus update we can in fact start actual calculus with limits of functions. Okay, so that we are going to do, and tomorrow again we have our upload. So tomorrow let's do ring theory exercises from Gallian. So that's just it. So I wrap things up for tonight. If you want to say something, you can write in the comment section below, and my mail address will be there in the description. So see you tomorrow with Gallian's ring exercises. Until then, this is me, Lucifer, from the mathematical room. Have a nice night.